Good day, everyone. Today, we will be discussing about the arc lengths of polar curves and the areas of polar regions. So first, let us have a recall about the arc length formula in polar coordinates. Suppose a smooth polar curve C that is defined by the equation r is equal to the function of theta is traced exactly once as theta varies from alpha to beta. Then the length of the curve is given by this equation. We have the length equals the integral of the square root of r squared plus the square of dr over d theta with respect to theta from alpha to beta. Next, the area of polar region. Suppose the curve C that is defined by r is equal to f of theta is continuous on alpha to beta inclusively, where it satisfies this inequality, then the area of the region enclosed by C is given by this formula. We have the half of the integral of the square of f of theta with respect to theta from alpha to beta. Or equivalently, this is equal to the integral of r squared with respect to theta from alpha to beta multiplied by 1 half. So you just have to shoot the value of f theta. Since our f of theta here is equal to r, we have this equation. So we take note of the following remarks. First, the limits of integration are determined by the radial lines or rays that bound the region. Second, most of the time, it is really helpful to take advantage of the symmetry of the given polar region. So these are the following steps in finding the area between two polar curves. First is to graph the polar curves to determine exactly how many intersection points should be there. Second, solve for the points of intersection of these polar curves. This will serve as the limits of the area of the integral. And then third, we just apply the formula for area of a polar region. So intersection points of polar curves are naturally obtained by equating the expressions for r. This is to simply get the value of theta so that we can get their points of intersection. However, this method will not always produce all the intersection points because of the many ways of representing a point in polar coordinates. Thus, it is a good idea to first graph the curves to determine how many intersection points there are. So for the first problem, consider the polar curves a CISA1 that is defined by the equation r equals 2 cosine of 2 theta, and the C sub 2 that is defined by the equation r equals 2 minus 2 sine theta, and this is their graph. So we have to find the points of intersection of C sub 1 and C sub 2. Now, to get the points of intersection of C sub 1 and C sub 2, we just have to equate these two equations and solve for the value of theta. So if we equate from the two given equations, we have 2 cosine of 2 theta is equal to 2 minus 2 sine theta. And since we have 2 from both sides, we can divide this out. So we get cosine of 2 theta equals 1 minus sine theta. And we know that cosine 2 theta from its identities, we can replace this by 1 minus 2 sine squared theta equals 1 minus sine theta, and then cancel 1 from both sides, and we can replace a negative 2 sine squared theta to the right side. And we will get 2 sine squared theta minus sine theta equals 0. Then, factor out the sine theta here, and you have sine theta multiplied by the quantity 2 sine theta minus 1 equals 0. So we have sine theta equals 0, or 2 sine theta minus 1 equals 0. So solving for the values of theta from sine theta equals 0, we get theta equals 0 or pi. On the other hand, from 2 sine theta minus 1 equals 0, we have theta equals pi over 6 or pi over 6. This is because sine theta here will be equal to 1 half. And we get these values of theta. Then, by evaluating r equals 2 cosine theta, at theta equals 0 or pi, we get r equals 2. So just substitute the values of theta here, 0 and pi, and you'll get the value r equals 2. You can also substitute these values to the other curve, that is r equals 2 minus 2 sine theta, and you'll also get the same value. Then we have 2 points of intersection. Those are 2 comma 0, comma 2 comma pi. Then on the other hand, by evaluating r equals 2 minus 2 sine theta at theta equals pi over 6 and at theta equals pi over 6, we get the value r equals 1. Then the points of intersections are 1 comma pi over 6 comma 1 comma pi over 6. So these values of theta, you can also substitute this to this one, to this curve, r equals 2 cosine theta, and you also get the same value, r equals 1. Okay? Note that while it may look like we must have a point of intersection, this is because from the figure, we can see that it looks like there is an intersection here, but however, there isn't, because there is no theta such that both r equals 2 cosine of 2 theta and r equals 2 minus 2 sine theta are both 0. Hence, 0 comma theta is not a point of intersection of c sub 1 and c sub 2. Therefore, the points of intersections are these points: 2 comma 0, 2 comma pi, 1 comma pi over 6, and lastly, 1 comma pi over 6. So for the next problem, consider the same polar curves, c sub 1 and c sub 2. Set up an integral equal to the following: the perimeter of one petal of c sub 1 and the area of the shaded region. So for the perimeter of one petal of c sub 1, note that the graph of c sub 1 is symmetric about the polar axis. So we make use of its symmetry and just set up the definite integral equal to the perimeter of half a petal, then multiply by 2. So in particular, we will be considering this petal, the upper half of the right petal, and we can just cut it up to half, and we can get the length or the perimeter of this region, and we will multiply it by 2. So theta here must vary from theta equals 0 to theta equals pi over 4. We then have the arc length that is given by 2 multiplied by the integral of the square root of r squared plus the square of dr over d theta from 0 to pi over 4. Then just substitute the value of r and the derivative of r with respect to theta, and we will get 2 multiplied by the integral of the square root of the quantity 2 cosine of 2 theta plus the square of the quantity of negative 4 sine 2 theta. So from 0 to pi over 4. So in this case, the derivative of r with respect to theta is negative 4 sine of 2 theta. This is because the derivative of cosine of 2 theta is negative sine of 2 theta, and by chain rule, the derivative of 2 theta is just 2. So you'll get 2 multiplied by the negative sine of 2 theta multiplied by 2, and you have negative 4 sine of 2 theta. So for the second problem, we have to find the area of the shaded region. So first, note that the graphs of c sub 1 and c sub 2 are symmetric about the pi over 2 axis. So we will make use of its symmetry and just set up the definite integral equal to the area of half a petal and the area of the region of the upper half of the right petal of c sub 1 that is inside the cardioid. Then multiply it by 2. Okay, so the area of the region of the upper half of the right petal of c sub 1 that is inside the cardioid is the area of c sub 2 as theta varies from 0 to pi over 6, and area of c sub 1 as theta varies from pi over 6 to pi over 4. So in this case, we have here this illustration. Okay, so the area of this one, of the shaded region, is given by theta varying from 0 to pi over 6. And the area of this region is given by theta varying from pi over 6 to pi over 4. Okay? Observe that the graphs may seem to intersect at the points where theta equals 0 or pi over 2. However, the rows and the cardioid have different values of r at theta equals 0, comma, pi over 2. Note that the cardioid varies from theta equals 0 to pi over 2, while the half petal varies from 0 to pi over 4. So to get the other half of a petal, we can just use the curve of c sub 1 from theta equals 0 to theta equals pi over 4. With the symmetry, we get this expression for the area. So we have 2 multiplied by the area of half a petal plus area of upper half of the right petal that is inside the cardioid. That is 1/2 multiplied by the integral of the square of the quantity 2 minus 2 sine theta with respect to theta from 0 to pi over 6 plus half of the square of 2 cosine 2 theta with respect to theta from pi over 6 to pi over 4. Okay, that is all for today. So I hope you learned from this.